equation for a thin lens is pretty much identical to the mirror equation. It relates the distance of an object to the lens to the distance of its corresponding image to the lens. And the equation is 1 over f, where f is the focal length, equals 1 over SO, where SO is the distance between the lens and object, plus 1 over SI, where SI is the distance from the image to the lens. Now, one thing that's a little bit different between lenses and mirrors in this equation is what's defined as a positive SI. So in this case, the refracted light rays actually do pass through the image, which makes this a real image on the opposite side of the lens. So when the image is on the opposite side here, the image is real and SI is positive. In the case where light doesn't converge on the opposite side of the lens, a virtual image is formed on the same side of the lens as the object. And for a thin lens, this is a virtual image. And just like with mirrors, a virtual image will have a negative value of SI. The magnification formula for a lens is also the same as a mirror. It's defined as HI, the height of the image, over HO, the height of the object. And again, this ratio of the heights is also equal to the absolute value of the ratio of the distances to the lens, SI over SO, where virtual images are upright and real images are inverted. The first question gives a converging lens with a focal length of 10, and there's an object with a height of 4, placed a distance of 15 centimeters from the lens, and it's asking for the location and size of the image. So the thin lens equation says 1 over focal length equals 1 over object distance SO plus 1 over image distance SI. And in this case, I have 1 over 10 equals 1 over 15 plus 1 over SI, which solving this gives that SI is 30 centimeters. Because this answer is positive, that means I have a real image, which means for a lens it's on the opposite side of the lens. And because the image distance is greater than the object distance, that means this image will be magnified compared to the object. And that ratio, HO over HI, is equal to the ratio of the image distance over the object distance. In this case, that's a ratio of 30 over 15, or 2 to 1. So the image is twice as tall as the object, which means it has a height of 8 centimeters. And I get an image distance of negative 6 centimeters. Now, because this is negative, it means the image is virtual, which means it'll be upright. And since this is a lens, that means the image is on the same side of the lens as the object. As for the size of the image, the magnification, HI over HO, will be in the same ratio as the absolute value of the image distance over the object distance. So the image height over the object height of 6 will be equal to 6 over 15, which gives an answer of 36 over 15, or 2.4 centimeters. The next question deals with the lens combination. And in this case, where there's 2 lenses, the image of the first lens is going to be used as the object for the second lens. So this question gives 2 lenses. The first one has a focal length of 10, and the object is placed a distance of 20 from the first lens. So the first thing I want to do is find the image from the first lens, which will be later used as the object for the second lens. So for the first lens, the lens equation says 1 over focal length, which is 10 for the first lens, equals 1 over 20, plus 1 over the distance between the first lens and the first image. And that's going to give an answer of 20, which means that the image is the same size as the object because it's the same distance. And because this is positive 20 and it's a lens, it's going to be on the opposite side of the lens as the object. And because the total distance between the two lenses is 35, it's going to be a distance of 15 from the second lens. So now I have an object distance of 15 and a focal length of 6. So for the second image, I'm going to use the first image as my object and have 1 over the focal length for the second lens, which is 6, equals 1 over the object distance, which is 15, plus 1 over the final image distance, SI. And solving that for SI gives a value of 10. And this is positive 10. Since the answer is positive again, it means the image is going to invert one more time. And it's also going to be a real image on the opposite side of the second lens as the object was, which in this case, of course, the object was the image from the first lens. So it's going to be 10 centimeters to the right of the lens and inverted again. The last question is a convex lens concave mirror combo. It works the same as the last question, where I'm going to find the first image created by the lens, which will be the object for the mirror later on. So for the lens, I have a focal length of 8 and an object distance of 24. So the lens equation says 1 over 8 equals 1 over 24 plus 1 over the image distance for the image created by the lens. And when I solve for SI here, I get a value of 12. Now this is positive 12, which means that this image is going to invert and will be on the opposite side of the lens. So it would be around there. Here my image distance is 12. So when this image here acts as the object for the mirror, it's going to be a distance of 20 from the mirror. Now when I find the second image, using the lens's image as my object, I have a mirror focal length of 12, and now this 20 here is my new SO. And here the mirror equation says that 1 over 12 equals 1 over 20 plus 1 over the mirror image distance. Solving this gives an image distance of 30. Because in this case I'm dealing with a mirror, and this is a positive number, it is a real image, so it will invert again, but this time, because it's a mirror, the real image is going to be on the same side of the mirror as the object. So it's going to be somewhere around here.